Hello guys, we are team 18. We are going to discuss about deadlock detection and my name is Ashik. I am going to tell about overview of the deadlocks in operating system. Welcome to our exploration of deadlock detection in operating system. Deadlocks occurs when multiple processes are stuck indefinitely waiting for resources held by each other, potentially halting system progress. This foundational concept is crucial for building reliable, efficient computing environments that computing science students and junior system programmers must master to ensure robust software and system designs. Now we are going to discuss about the four necessary conditions for deadlock. First is mutual exclusion, second is hold and wait, third is no preemption, fourth is circular wait. In mutual exclusion, resources can only be held by one process at a time. They are non-shareable, preventing simultaneously access and setting the stage for conflicts. Now, second one, hold and wait. A process holds some resources while waiting to accuse others, creating dependence that can escalate into broader waits access the system. Now, third one, no preemption. Resources cannot be forcibly removed from a process. They might released voluntarily or limiting the OS ability to intervene dynamically. Now, fourth one, circular wait. Processes form a cycle where each waits for a resource held by the next, closing the loop that traps the system in deadlock.
Hello guys, this is Abhishek Deep and I'm taking over from my teammate Ashik. So we will start from fourth slide. In this graph, each process is a node, and an arrow from one process to another means it's waiting for that process resource. The OS checks this graph for cycles usually with a depth first search algorithm. If a cycle is found, it means those processes are waiting on each other and the system is in deadlock. By detecting these cycles early, the OS can identify which processes are stuck and recover before system performance is affected. Moving on to the next slide, slide 5, handling multiple resource instances. The OS uses three main data structures. The allocation matrix shows what each process currently holds. The request matrix lists what each process still needs, and the available vector tracks how many units of each resource are free. With this information, the OS can simulate which process could finish and which ones might cause a deadlock, and even when resources are shared among many tasks. Moving on to the next slide, slide 6, detection algorithm step by step. First, the OS initializes a work vector with available resources and a finished array for each process. Then it searches for any unfinished process whose request can be met with the available resources. If one is found, it's treated as finished and its resources are released back to work. The system repeats until this no more process can finish. And any process still marked unfinished at the end is considered deadlock. Moving on to the next slide, strategies for deadlock recovery. It can use resource preemption, temporarily taking resources from some resources to free up others, or it can use process rollback, returning a process to a previous checkpoint so it releases resources safely. The final option is process termination, completely ending one or more processes involved in the deadlock. The choice depends on each which method causes the least disruption to the system. Moving to the last slide, challenges in distributed deadlock detection. There's no shared memory, and communication happens through network messages, which add delays and the risk of failure. Without a single global view, detecting cycles is difficult. That's why distributed systems rely on specialized algorithms, like probe messages and coordinated checks, to identify deadlocks across the network.
Hello all, I am Arjun and I am going to take the key algorithms for distributed detections. There are three methods. The first one is centralized approach. A detected coordinator node collects local weight for graph from all sides, build a global graph and detect cycles centrally from symbol management. Second one is distributed technique. Path pushing sends probe message along weight paths. Edge chasing propagates edge to find cycles. Diffusion computation flood the network to trace dependencies. Third one is hierarchical method. Combines local cluster detection with global oversight, reducing network traffic by handling subsets first before escalating to higher levels. Mastering deadlock detection for reliable system. There are three. First one, core insights. Deadlocks are detected via wait for graphs for single instances and metrics based algorithms for multiples, enabling timely identifications in OS environment. Second is recovery essentials. Strategies like preemption, rollback, and termination restore operations carefully chosen to minimize disruptions and preserve system stability. Third one, distributed advance. Algorithms such as centralized coordinations and edge chasing handle network scale challenges, scaling reliable for modern distributed computing. So there is a practical example in MySQL deadlock detection. In real-world databases like MySQL, deadlock detection is integrated into transaction processing. During concurrent operations, the InnoDB storage engine monitors wait for relationships. If a cycle is found, such as two transactions each locking a row the other needs, MySQL automatically selects and rolls back the transaction with the least cost. Based on factors like undo, log size, and active time, this ensures database responsive, prevent indefinite hangs, and maintain data integrity in high traffic production environments.
Ensuring reliability, complex computing environments. From OS system throughout this session, deadlock detection stands as a cornerstone for ensuring reliability, complex computing environments. From OS systems to distributed databases. Understanding how to identify and resolve deadlock helps build systems that are resilient, efficient, and trustworthy. Thank you for engaging with us and for your commitment to deepening your knowledge in computer science. Wishing you great success as you apply these concepts in your own work.